Hi everyone, welcome back to another video, an update on the engine. So today we're talking about grass. So I've been following me on social media, YouTube, whatever, you probably know I've been posting quite a bit of stuff about grass because I've been working on it, and now is a good point where I can consider the first phase done and I can move forward, and I wanted to share what I did. So this is the result. So we have grass waving down, and there is quite a bit going on here. So first of all, I implemented a double camera. So one is considered the main camera and one is considered the active camera. So what this allowed me to do is to jump one camera to the other, right? So you see I have two cameras. This is the main camera, and this is the active camera. I'm flying around so I can see the frustum. I'm drawing the frustum, so these were really useful for the culling. So you can see I have frustum culling going on. So if I'm moving around here, you can see now all those tiles of grass have been culled. And not only that, there is also LODding going on, and you can probably see it because, like this, you probably look at here, you can probably see the popping of the new tiles going on. But let me show you directly a bit more. So let me enable this is debug though, so there's a lot of ifs, but it's just, you know, it's debug. So if I recompile the shader, so grass forward, so if I recompile it, now we should basically see the culling, sorry, the LODding going on. Oops, sorry. Here we go. So those are the three different levels of cascade of the LOD. Of course, those values are arbitrary, and once you have a scene, you start playing with those, something that makes sense. So if you have the camera roughly this height, you might want LOD1 to be a bit bigger, but of course you're gonna stretch those out. But you can see how it behaves, right? And basically the way it works is that I compute the LOD value for each tile, and then based on the LOD value, I can decide how many points I'm gonna have for that LOD. Sorry, how many blades I'm gonna have for that tile for the specific LOD. And I picked the points in a specific way that I'm going to explain a little bit more how the actual grass work. I just wanted to see what it does. So let me just put the shader back to what it was really quick. Let's compile it again. There we go. So we're back in business. So there is, of course, I have a tool. Let's remove some clutter here. So you can change all the parameters. I think I showed that already. You can change the band, you can change the grid, how it is, you can change colors, you can change stuff. But what I want to talk about now here is the LOD configuration. So you can probably see when I change this changed the distance where the actually let's go back to color. If I can scroll, let's go back to color really quick, just because it's gonna make our life easier when I show this. So I can move the distance of LOD1, right? Then LOD2, of course. So I can have different distance, but then I can also change. Oops, sorry, that's still the LOD. I can change the number of blades per LOD. So you see when it's red, so LOD 0, he has 500 blades, 300, 200, 100. And I can change this. So you see it's getting denser and less dense. So you have full control. You can play with that as much as you want. So let me put the shader back to what it was. There we go. Let's compile really quick. There we go. So you can see, let's get closer here. There we go. Right, so you can change the density of the patches. So you see that points are not moving around. So for example, you see this blade is always gonna be there no matter if I add or remove. So the points are not jumping around. And this is something I saw specifically in order to have LODding done in this way. So I'm gonna explain this a lot more in details in a blog post that you can find in the description. But here is a quick rundown of how the whole grass works. So I generated some tiles of blue noise points, and that's really important, and we're going to see in a bit later. So I generated about 100 different tiles of 10,000 points each. which the algorithm I used to generate those points is not the most efficient. So it took around 3 hours on a 6-core machine, but I just let it run, do its own thing. It was a laptop, so it was like screaming at me, but this data is basically baked down. You do it once and that's it. Then what I do is that I give a random ID to each of these tiles between 1 and 100. And the distribution is quite nice. The blue noise is not actually tileable, but it's hard to see because there is so much grass. And the distribution is nice. You don't really see discontinuities. So each one of these tiles you see here is going to pull points out of one of those 100 tiles of blue noise points I've generated. So that's cool. I have my grid. Then what happened? I kick a compute shader. The compute shader, then we can actually see, is the scan, as actually here. So what it does is going to do the frustum culling. So if the tile is visible, then it's going to compute an LOD, and then it's going to do basically a scan and compat of this data, and then basically get an array, four different arrays per LOD of tile that survived. So first array, all the tiles, the LOD1 that survived in a compact array. So then I use that to populate a drawing direct, and then I kick 4 drawing direct, all from the GPU. So you can see that all the grass rendering is completely GPU driven, from the culling, to the LODding, and everything. Now, why was the blue noise key? So I wanted to find something that allow me to easily scale the density of the grass. And of course I didn't want to use geometry shader. I wanted the points to be stable. So talking to Alan Wolf, which has been helping me for now, how many years now? I don't even know. The guy is amazing. I've been having like at least 6 years or something, been nerding about graphics. So I came to him to the problem and say, okay, I need these points with this kind of distribution that if I get a subset of them, they are going to be still well distributed, because my core idea for the LODding is simple. I have 100 points that I want to render for the highest LOD, but if I have 2 LOD lower, I want 50% of those points. And if I grab 50% of those points, I still want them to be well distributed. That's why then Alan suggested, okay, go with blue noise. I went on his blog, I grabbed his C++ code for blue noise, I generate those points, and it's working really well, as you can see. So that's what I do. So I just say, okay, grab these many points, and we define it here. So from the 10,000 points in the tile, grab these many points. So probably 10,000 is a bit too much. I still need to find the right balance. Of course, the tiles, you can make them bigger with more points, but then the culling becomes less granular. So there is a lot of room for experimenting in there. But that's how it works. The blue noise distribution was key in order to have the LODding done in this way. It's all Vertex shader. So I can show you the Vertex shader. So there is a grass expansion, Vertex shader. So this is heavily based. So the base of the waves of the grass, how it moves, is from Royston. I hope I'm not butchering the name, but there will be a link in the description in the blog post. It basically uses a geometry shader to create this grass. Instead, I go and I use Vertex shader. So I know how many points I'm gonna have per blade. I use the vertex index. I do all the computation to figure out, okay, which vertex I'm on, which blade I'm on, and then from there I just spit out the correct points, right? So it's all done in a Vertex shader. I compute various matrices to rotate the grass, all the stuff that we showed before, but it's all Vertex shader, so it's quite fast. It will be interesting to see how a geometry shader behaves, because there are quite a bit of a trade-off here. Because sure, Vertex shader usually is faster to do these kind of things, but you can see I'm computing a lot of matrices, right? And those matrices are invariant per blade. It means if I have 15 points per blade, I'm going to compute this value 15 times the same time. So you know, it's quite a bit of computation, maybe we can say, but to be honest, we really need to see where we are bottlenecked here. So let's actually have a look at the performance of this shader. So we can see here the whole frame here is rendering 2 milliseconds, the whole thing, but I took captures, so we can actually have a look here. Those are 3 different captures using the Radeon profiler. So this was the original grass. I was rendering 40 million points brute force, no culling, no loading, and it was taking 0.7 milliseconds. So it's mind-boggling how fast GPUs are today. But there is a big problem here. So you can see green is vertex shader, blue is fragment shader. So all this is grass. So number 23 is grass. So you see there is a stupid amount of vertex shader. So especially here, half the draw call is just vertex shader, vertex shader, vertex shader, which actually does not generate any fragments. So there is a ridiculous amount of overdraw and wasted work. So that's the first things. And I also took Insight graphics capture, and rightfully so, as expected, basically I'm rasterizer bound, especially viewport clipping bound. Basically the rasterizer cannot keep up with the number of vertices I spit out, and then those vertices don't contribute anything. You can see that basically pretty much here what's happening is that early depth is discarding those fragments as they don't even contribute. So there is zero invocation of fragment shader in there. So okay, sure, let's start with the frustum culling, and this helps a lot greatly. Okay, so we already have halved the cost, and we can see that now the distribution is not too bad. Still, vertex shader is not doing crazy, but it's going quite all right. It's for sure we removed pretty much all this useless work, right? And you can see that's pretty much half of the draw call. So that's pretty much where our speed up is from. So great. Then we add the LODding, and you can see that now we have 4 different draw calls. Actually, number 22 is because the 4th LOD is rendering nothing. So it's an empty draw call. It's not ideal, but in our use case wouldn't happen. But you can see, so we have the 3 draw call from indirect, and the total is around 0.15 millisecond. Of course, the loading was quite aggressive, so in reality the speed up might be a bit lower, but still you can see that now it's faster and there is a bit more fragment work done. Sure, it can probably be improved, but probably now we are not so bound anymore on rasterizer. I actually need to check that. So we can see there is quite a bit of vertex work, and maybe we can speed up. Maybe we can optimize the shader. That's where maybe geometry shader might be viable. I honestly never wrote a single line of geometry shaders, so I don't know. But I'm really not dying to try. I'd rather focus on something else. But it was interesting to see how the shader transformed, and there are going to be more details in the blog post, so I suggest you to check it out. But this is it. And of course, now this also works in DirectX 12 as is. So actually we can probably do that. So let's change this to run in DX12. I need to run CMake, so it's gonna copy the configuration over. But now, so this is running, you can see from here, it's running in DX12, and you can still see the popping going around. So the culling is working, so you see there's a whole culling there and so on. So it's working as expected. So this is the current state of the engine. One big thing was that I decided I was tired to rewrite HLSL shaders. So what I end up doing is I integrate a Spear V cross into the engine. So I only write GLSL shader now, and then I transpile them to HLSL. Now the engine still try to look for native HLSL, If it doesn't find it, it tries to look for a transpiled one. So I still have at any point in time the the ability to drop in an HLSL shader and it basically will work. But so I have a JSON file that I use basically to control the compiler. So this is just a bunch of commands that my resource compiler is going to do. And in the case of shaders, we can see, so here is the grass expansion, right? So I'm gonna compile it. It's a Vertex shader, it's a Vulkan shader. So this is the plugin compiling it. But then what I also do, actually here, so I compile it also to spv.hlsl. So the compiler check, if it ends up with spv.hlsl, it's going to invoke SPIRB. But then I basically feed this output file into the shader compiler plugin, which is actually the DX12 shader compiler. So I'm chaining compilers to do all the transpilation, and basically, boom, out of here you have a proper DX12 shader. So it forces me to change a bunch of things. I had to change how I bind my meshes, my data, because by default SPIRB cross uses byte address buffer instead of structure buffer, but it uses structure loads. But the way you create SRV is slightly different, so I had to fix that, and I had to fix other stuff that now I don't remember, but it's so much better. I can write the shader once and it works. And also I'm quite happy the engine is getting to a place where I can focus more on what I want to do. There is enough abstraction that is going to work both in Vulkan and DX12. So I'm quite happy about it. So now I can move forward. I want to add more to the scene. So probably next is gonna be trees. Then I want to work on shadows, so cascade shadows. I want to see what to do shadow-wise for the grass. Is the grass itself gonna cast shadows? Is it even worth it? Is it even gonna add much in this case, in this kind of grass? Or is it just gonna receive shadows? So that's what I'm gonna work next. So this is an update on the state of the engine, and I'm quite happy with how the grass turned out. And it was a quite nice experiment to try this blue noise distribution for the grass. As usual, if you like, subscribe, share, and if you want to stay up to date with the channel especially, and see you in the next video.